everyone. Thank you for joining us for our AEE member webinar. Before I introduce our speakers, I want to go over just a few announcements. Following the webinar, you will receive an email with a certificate of attendance and a recording of the webinar. If you're interested in obtaining a copy of this presentation, please email me at shannon@aeecenter.org. We will be doing some Q&A following the presentation, so please place any questions that you have in the box in the side panel. Without further delay, I would like to introduce our lead speaker, Gary Peterson. Gary has been introducing disruptive technologies in the energy space for almost 30 years. He is instrumental in developing creative energy solutions that deliver business and operational results. And without
Thank you,
further
Shannon.
ado, I will hand this over to Gary.
Thank you, Shannon. Real quick, I don't want to spend too much time for me talking. I want to pass it over to Carson here shortly. But over the years, most of us, if not all of us, have walked through manufacturing facilities and we're told not to touch the production line because they did not want to go ahead and have any anomalies that maybe the engineers have done from an energy conservation perspective. But as you'll see in this presentation, TwinThread allows us to positively affect the manufacturing process from an energy conservation perspective. So with that, I'd like to turn it over to Carson Drake. He is the co-founder and vice president of GrayMatter, which is an integrator for TwinThread. So Carson, it's all yours.
All right. Thanks, Gary. Can you guys hear me okay?
Yep, we can hear you.
All righty. So Shannon, I'll share my screen. Did you want to unshare? Thank you. Awesome. Okay. Technology is wonderful. Okay. My main job today is to introduce you to Erik Udstuen. What I wanted to do first was introduce you to my company, GrayMatter. GrayMatter was founded in 1991. I was one of the co-founders, and we started out in the controls business. Prior to GrayMatter, we were putting in control systems that were based on mainframes, and we saw the IBM PC coming and the programmable logic controllers coming, and so we created a company called GrayMatter in 1991, and we kind of really started down at the machine level, putting PLCs and PC-based HMIs and SCADAs on control systems. And when Microsoft Windows hit, that's when our company took off. And we've been in over 10,000 manufacturing plants. And we have a combination of consulting where we help create strategies and consult on processes and so forth. We also have implementation services. We've got about 120 people in the company. And then what we're going to talk about today is some new technology. We bring technologies to bear. We're manufacturers reps for various technologies. And one of the things we do is we curate new technologies. So we survey the market and go out and try different things with our long-term customers. And then once we find something that's a winner, we bring it out to the masses, to all of our customers. So that's kind of our background. We've interfaced with PLCs, BACnet and LAN in the building management systems, working on industrial equipment, including energy type equipment, chillers, boilers, facilities metering. There's a term you'll hear today called WAGES. It stands for water, air, gas, and electricity and steam. We're doing a lot of work in that area, particularly in this machine learning and predictive analytics space. So that's what we're going to do today. What I thought I'd do is kind of position this a little bit. Many of you have heard of this Industry 4.0. It's a term that was coined out of Europe. Here in North America, we call it the smart factory often. And it includes a lot of different things: manufacturing execution systems, Internet of Things, sensors, analytics, cybersecurity, 3D printers, augmented reality, virtual reality glasses, collaborative robots, and so forth. What we're going to talk about today is, in particular, these three things: this industrial analytics space as applied to energy and facilities. So we're going to talk about IoT and analytics and machine learning today. That's where we're going to focus. There's a lot of momentum in this space. I thought I'd bring this Gartner hype curve up. There's a lot of hype. And in this curve, this curve shows sort of new technologies. There's an innovation trigger that occurs, and then things get sort of percolated. That's that technology curation curve that I mentioned. And then you see down here on the bottom, you kind of reach this peak of inflated expectations. So you'll see automatic machine learning here. And then as people get into the new technologies, you'll see sort of this, they call it the trough of delusionment. kind of sounds like a Grateful Dead concert or something. But a lot of people are trying this new technology and they're not having success. And that's where we come in. We kind of get you through this part of the curve and get customers up into the plateau of productivity. So I thought I'd bring this curve up. It's kind of fun. But yeah, there's a lot of excitement in this space. There's a lot of momentum, and that's good and bad. If you look in this analytics space, there's a lot of companies, there's a lot of venture capital, there's a lot of people building tools and a lot of different approaches. There's probably over 500 companies in this machine learning and industrial analytics space, and IoT platforms and smart sensors, spooling data to the cloud and so forth. And we found a winner. When we go into this TwinThread technology, I'll turn it over to Erik after just one more slide. We found something that's really unique, and Erik will illuminate why that is and how it applies to this particular space. So I'm going to introduce Erik. I'll start with Erik Udstuen, and he is the co-founder of TwinThread, and he's been in the business for over 25 years. He actually built a company, he's built several companies, and one of the companies that he's built was for manufacturing execution and analytics inside of the manufacturing plant. And he had that company acquired by General Electric, and actually ran this division of General Electric that we work with called GE Intelligent Platforms. It's now called GE Digital. And while he was there, he started to get into this predictive and advanced analytics space. He actually bought a company called Smart Signal, and it was based on some older technology, some older approaches. And he built a $100 million data center down in Atlanta, and it still is monitoring over 1,500 gas turbines around the world. All that data was spooling into the Atlanta data center and doing predictive analytics on gas turbines around the world. And the epiphany that he had was that most companies can't afford a $100 million data center, and the tools were difficult to deploy to the masses. So his effort with TwinThread was to create this concept of a analytics operations center out of a box, based on modern tools, based on cloud technologies, and really make it configurable by the user as opposed to putting together different pieces, parts of cloud technology. And I'll let him go into that in more detail. But been working with Erik for many years, and he's one of the masters in our space. And looking forward to introducing you to this technology that we've curated and now are taking out to the masses. Lots of big customers on board. TwinThread's already monitoring over 1 million assets today. So with that, I'd like to turn it over to Erik Udstuen.
Thanks, Carson. Hi, this is Erik Udstuen. I'm going to try to share my screen here quickly. Okay. Get the right screen shared. Let me know if you can see that.
Yep.
Excellent. Well, thanks again, Carson, for the introduction. We're really excited to present to this group. You're working on a problem as a group that we're very, very interested in solving. That is, driving energy efficiency, particularly within industrial manufacturing operations. And so some of the things that I'm going to talk about today are, first of all, some modern tools for the industrial energy professional look like, at least what we see, and some of the requirements that we see to really be able to scale this technology out, as Carson described. And then we'll get into some specifics about how advanced analytics can drive energy savings in that industrial environment. And as Carson mentioned, this isn't just about the facilities and let's say the supporting infrastructure that you find within an industrial plant or complex. This is about how you can actually tune the process to deliver high quality product at highest throughput, but with the lowest energy footprint. And this is pretty exciting stuff. The last is just some pointers from our perspective on how you create a sustainable and scalable program. As Carson mentioned, I spent a number of years with General Electric, and it was certainly General Electric's mantra to not just drive a 2% savings or 5% savings this year, but the expectation is to continuously drive incremental savings year after year after year. And we'll talk a little bit about some of the keys to creating those sustainable programs that work for years. From my perspective, obviously analytics is driven by data, and there's all this hype in the market that Carson mentioned about using data and applying it to solve all kinds of problems, from autonomous vehicles all the way through to optimizing a commercial building or optimizing a manufacturing facility. But it's not really data you need. You actually need applications. And here's why is, as an engineer, I don't want to spend time on collecting data or managing and curating, filtering, and perfecting that data. I also don't want to spend time becoming data scientists. What I want to do as an engineer is I want to apply my expertise and in the domain about the equipment, about the processes. And I want to spend my time on establishing what the right metrics are to drive improvements, building the business cases around those improvements, and most of all, using my expertise in the equipment, in the processes to innovate. And really having the right software tool to support you is critical. And the right software tool should magnify your expertise and not expect you to become a data scientist, for example. If you're an engineer and have expertise in the equipment and processes, really it's most efficient if you can just apply your expertise straight away and not have to learn a whole new domain in terms of data science. So with an industrial predictive analytics platform, you can innovate around how equipment and processes are planned, operated, optimized, and maintained using algorithms and data. And data is obviously the important ingredient for any of these programs, as we talked about. But I want to highlight it's the algorithms that really make the difference in scale. With the right platform in place, it should be able to identify the exceptions and the opportunities for improvements without having someone monitor it as an individual 24/7 to find those opportunities. So it's the algorithms that really coax out the opportunities for savings. So by having something like a predictive operations platform in place, you should be able to collect data from all the assets involved. And this isn't just the facilities-based assets like the HVAC system, for example. This is the actual process equipment and everything that you find within the four walls of an industrial facility. To be able to automatically monitor those processes, automatically look for opportunities for improvements using advanced analytics and machine learning, and then get the right engineer involved at the right time to either solve a problem or capitalize on an opportunity. And this is really what this predictive operations platform is all about. So as I mentioned earlier, it's not just about the data, it's about having applications. And by having applications that have been purpose-built to solve specific predictive problems, this is the difference between being able to take a tool and apply it and get benefits straight away, or having to build it and learn and to spend a lot of time on potentially R&D efforts that just delay the benefits and dilute the return on investment. So this is why we think it's really important to go straight away to applications. As TwinThread, we offer about 25 pre-built predictive applications that can be applied out of the box. The 6 that you see on the screen here are kind of the workhorses, the most popular, most widely deployed, and most common, addressing the most common problems that you find within an industrial facility. Everything from predictive quality and throughput, and predictive energy efficiency, which we're going to drill into detail today about. Those are all sort of operational problems that typical industrial facilities have. And then there is the predictive uptime, asset reliability, predictive asset life. These are kind of the maintenance domain related problems that you find within an industrial facility. And again, we offer these applications out of the box so that customers can get to value straight away without having to build and learn. So as I mentioned, we're going to focus today on predictive energy efficiency. And as Carson mentioned earlier, this isn't just about electricity. This is in fact about all the utilities that you find in a typical industrial facility, from water, air, gas, electricity, and steam. And there's maybe some nuances across each one of those utilities that are important to address. But the overall goal, if you will, of predictive energy efficiency is to drive savings in all of those utilities across the facility and across the production processes. So when we think about the platform and being able to deploy an application directly out of the box, there's a couple technical challenges that platform needs to solve so that you can get straight away to the benefits. And the first, maybe obvious, is that the platform needs to collect data from a variety of different data sources and across a variety of different protocols. It wouldn't be atypical to walk into a facility where there are a dozen different protocols and different data sources that are necessary to get a full picture of the energy consumption across that facility. And often this isn't just about collecting data from meters. This is also collecting all of the process data that is really driving the consumption that's being measured by those meters. And as I said, often we find dozens of different protocols and different data sources that give you that full picture of what's going on in that facility. The next piece is creating digital twins. As the name TwinThread suggests, the digital twin is really, really important to enabling all of the analytics that we're going to talk about today. And so this is often the first step in putting in that predictive operations platform, is modeling the digital twins. And the digital twin really just gives you a virtual representation of each of the key assets within a facility, so that you can perform at the simplistic level, so that you can perform metrics and calculations about how those assets are performing, whether it be from an energy or other dimension. But also the models that describe and predict how those assets are likely to behave under certain conditions or at a certain time. So the digital twin is kind of the foundation for everything. And then another thing the platform has to do out of the box is give you a way of monitoring, first defining the key metrics, and also monitoring those key metrics automatically. You can imagine our largest customer has several 100,000 assets, and they're able to really monitor the performance of those assets using only, let's say, 2.5 full-time equivalent resources. And really the only way that you could do something at that scale is by leveraging key metrics and algorithms that are monitoring those automatically. And just to forward alerts to the right people at the right time to solve problems and to address opportunities is a key feature that really needs to be available out of the box. This next piece that really needs to be there out of the box is to give you as an engineer the ability to innovate, not by having to write software or to try to translate requirements to a data scientist or translate requirements to a software developer, but rather give you an environment that you can develop new applications, new metrics, new actions in the process through this drag and drop and connect the dots development environment. You may have heard this as called a no-code or low-code development environment that really opens it up for a much wider audience to be able to innovate. But most importantly, it allows you as a domain expert or an expert in a piece of equipment to apply your knowledge directly without having to go through other resources or other tools to apply that. And we think that's a critical element for success. And the next piece is being able to deploy sophisticated models without development. So this is sort of the next level of innovation, to be able to not just create digital twins and the metrics and let's say key metrics around those assets. It's about being able to build predictive models and deploy those against your digital twins and against your equipment without having to develop. And as we'll see in a moment, there are many byproducts that come from having a good, accurate energy model about a particular process, a particular production line, or an entire facility that come from having deployed these models. And the platform needs to be able to deploy those out of the box in order to get extract the value from those. So next, I'm going to talk about a specific case study here. And here, this is a very large consumer products company that is in, I think, a very small group of companies in terms of size and also in terms of their commitment to sustainability. So they have made the commitment to reduce their energy footprint on a global basis across more than 100 manufacturing facilities by 5%. And that, again, spanning that wages, water, air, gas, electricity, and steam. And so this is a significant commitment, but also moves the needle in a very significant way in terms of the energy footprint for the company. such that if every consumer products company made the same commitment, this would have a very significant impact on the energy footprint of the world. And this is something that's very exciting for us and very exciting for our team to be working on and to get behind. So what this company did was they developed using the TwinThread platform energy models for each of their major process types. You can imagine in a large industrial facility, there are a number of different processes across making, converting, packaging. Each has different nuances in the consumption of energy. Each has different operating constraints. And the goal was to create these predictive models and apply them in a generic way, in a scalable way across thousands of assets, and do that quickly and painlessly. The overall goal is to really establish what's the best way to run the equipment that makes the best product and does it at the highest throughput, but also does it at the lowest energy footprint. These are very complex processes, and it's not too hard to imagine that there are many opportunities to just run a little bit differently, a little bit lower temperature here, a little bit higher pressure there, that all adds up to significant savings. And on top of that, much like reminding your children to turn off the light switch when they leave the room, there's also a set of procedures, obviously more complex than that come into play when not running equipment, when you've shut equipment down to do product changeovers or shut equipment down to do maintenance, that the procedure about shutting down and also about starting up can also have a significant impact on energy. And just simply leaving stuff running when it doesn't need to be running is simple, but often gets complex in a real industrial scenario. And that's where the analytics come into play to really provide good advice on how to operate the equipment, how to shut down the equipment, when to shut down the equipment, how and when to start it up, all with the goal of reducing energy footprint. And the payback from going through this exercise is significant. So we've seen payback periods from 11 days in a minimum up to, let's say, 60 or 90 days a maximum. And this is significant in that this is really just using data and applying software, and in fact even using tools in the cloud. So the upfront investment required in infrastructure, if you will, to go and capture those savings is really minimal, and that's reflected in the payback periods for what you can get out of this. It's very significant. So some of the strategies, just to kind of highlight some of the things that I briefly mentioned of generating savings in this way, is first identifying the best recipes for running equipment. And as I mentioned, sometimes these processes can get quite complex. It's hard for a human, frankly, to analyze all the dimensions to really get at what is the optimum recipe. If doing that manually with the data would be next to impossible. And that's where the machine learning algorithms and the cloud technology comes into play, to be able to make that not only practical, but to do it very quickly, to find what is the best optimum recipes. And in a nutshell, what the process behind developing or identifying the best recipes is identifying over the last year, or maybe it's 2 years of running on this piece of equipment for a given product, because many of these production lines produce different products on the same equipment. So it's necessary to look at this on a product by product basis. But let's say looking at 2 years worth of data, identifying not only where was the energy footprint best, but proving that it's actually a sustainable way of operating is kind of the key behind this, so that those recipes that are determined by the algorithms can then be practically deployed, because in fact, we're proving that the equipment has actually run like that for a sustained period in the past. Therefore, it should be able to run that way for a sustained period in the future. And of course, the other element of this is it wouldn't make sense to optimize energy around poor quality or reduced production rates. You know, the economics of poor quality and poor production are always going to outweigh, frankly, the economics of energy. And so it's really critical that those best recipes are developed based off of only the best running times, and maintaining that quality and throughput is essential to maintaining the economics of the gains around energy. The second piece I already mentioned at a high level is identifying the best procedures to shut down and start up equipment. Oftentimes, what you'll find is that there are, in terms of downtime events on a production line, sometimes there's micro stops where there's only a short outage or a short stop that the intent is to basically get back on production immediately. That might be a couple seconds, that might be a couple minutes. And then there are medium-term unplanned downtime events that can happen, where it's not just a few minutes. The equipment is down for an unknown amount of time, at least ahead of time. It's not known, but it's longer than a short shutdown. And then of course you have planned shutdowns for an extended time period where, for example, maintenance may be done and so forth. And so part of the trick here is identifying a different set of procedures for each set of those cases. What should happen during a micro stop? What should happen during a medium unplanned stop? What should happen when it's a planned and an extended stop? And identifying what's expected in those scenarios. And then of course, the whole secret is just alerting the operations team when those procedures are being deviated from. When something that was intended to be shut down is being left on, that's an opportunity to save energy. And depending on the process, that can be very significant. The third and probably the most obvious strategy where energy savings come from is simply benchmarking and comparing the best performing lines and products against the worst performing lines and products, and not just seeing that there's a difference between plant A and plant B, or line A and line B. It's actually having the depth of the analytics to understand why that is. What is causing line A to consume more energy on the same product at the same production rate? What's different? What are the differences? And by understanding those differences, it can be sometimes some of the most obvious changes that are made to the process to reduce energy. And so this is both maybe the most basic, but also potentially the most powerful element here of generating energy savings is around that point. And the last point is about that commitment to energy savings, and really not just committing to apply analytics and learn what the best procedures are, or learn what the differences between the best line and the worst line are. It's really using the analytics to generate anomalies and alerts that how those anomalies and alerts are dealt with is built into the operating regime, whether that be a daily production meeting to review yesterday's deviations in energy, or whether it's an actual real time, putting an alert in front of an operator that tells them they're running in a higher energy state right now. And these are the 3 reasons why you're running in a high energy state, and committing to make the process adjustments to reduce energy. This is really the critical element. It's one thing to provide analysis and provide insights. It's the payback doesn't happen until action is actually taken. And this 4th step is really about building those actions into the operating regime, the operating strategy, so that the savings can be captured. So a little bit more on the process and how this works. And this, what we're going through here, it would be the same if we were working on an energy problem as if we were working on a quality problem or potentially a throughput problem. The same process applies at a high level for any of those problems. And we see the first step is building the foundation for the analytics, which starts with building out and connecting those digital twins so that you have this virtual representation of the assets, how they're performing, all of the sensors that are associated with that equipment, all being part of those digital twins. Then we can apply an energy model and train it. And those 2 things in combination, the digital twins and the energy models that are running against those digital twins, form the foundation for generating energy savings. The second step is after training models, those models are going to learn a lot of things about, from an energy standpoint, how that process is operating. And inevitably, there are things that come from the analysis of what the models have learned that are going to be obvious. Like there's going to be an obvious set of top energy drivers. And then there's going to be surprises. There are always surprises that come from this second step of analyzing what the models learned. There's always a surprise in what's driving energy, whether it's the absolute top energy driver or whether it's, maybe the 6th or 7th in the top 10 list. There's always a surprise. And out of this process also comes that best recipe that we talked about, as well as identifying best operating procedures, as well as the benchmarking. So all we've done up to this point is train some models based on historical data coming from the digital twins. We haven't actually deployed a model or done anything in real time. We're just simply looking at what has the model learned. And these are things that you can take and apply directly. You don't even have to take it any further than this. You could take the best recipe and put that in action. You could take the information you're getting out of benchmarking one line versus another, or one product versus another, and you can take that directly into action. But aside from that, really the goal here is to establish the business cases. Where should attention be focused to drive the highest energy savings? For example, within that top energy driver, there may be a set of known and unknown, or previously unknown set of drivers, but not all of those are controllable, and not all of those have an opportunity to actually improve. So part of this process is really understanding what are the top drivers, but also what are the top drivers that could actually be manipulated or improved, and what is their impact on energy savings. And so this is really just about establishing a priority list of energy problems to go solve, and a priority list of business cases that are going to save energy. And those business cases can be just straight updating a recipe, which, there's no capital investment required to do that, but they could also be identifying an opportunity to put in additional sensors or additional control loops or automation. There might be some capital investment involved in that. But the output of this step 2 is really getting a clear picture on where the savings are and what the priority list of problems is to go tackle. And out of the platform, we provide a whole bunch of analytics to really make that simple and direct to get at what are the business cases. The next step here is to operationalize the results. This is about taking the models that we just analyzed and actually deploying them to the digital twins. So they get attached to those digital twins, and they run in real time looking for anomalies, also predicting what a future energy might be, so actually forecasting, and also sub-metering. It's worth mentioning that oftentimes in an industrial facility, there'll be meters, let's say at a certain level of equipment. You may have a meter for a line, but you don't have a meter on a filler or a case packer or a palletizer. So the individual pieces of sub-equipment on a line, it may not be easy to get at what is the energy consumption kind of down at that level. And so one of the outcomes here of deploying models to your digital twins is you can actually get software-based sub-metering. So without having to install a physical meter, we can use the predictive model to predict what is that sub-equipment consumption potentially, and to be able to use that in further analytics and so forth is often key. So all those things about operationalizing the results, building the anomalies, building the predictions into the operating regime for that line or for that plant. And this is how the actions are really driving energy savings. And here again, there's a series of screens and tools and tactics for integrating those predictions and soft sensors and so forth into whatever the operating regime is of the business. And then the last thing to mention here is that this is a continuous process. This is something that you don't do once. In fact, you would continuously retrain models, typically, let's say on a monthly basis or perhaps a weekly basis. It's really going out and capturing the new learnings that have happened as changes are made to the process, as adjustments are made to really capture the latest and greatest learning about what's going on in that facility, and repeating that process and reanalyzing the models for new insights and reprioritizing business cases and reprioritizing opportunities based on the latest and greatest state of the equipment and the processes. And that's really critical to the sustainability of the energy savings that can come from applying the models. So one of the things that we found is super valuable is that after you've gone through the trouble of creating digital twins and building out these energy models that are describing the energy consumption down at a very granular level in the facility and in the process, there are many uses for that energy data. Of course, there's benchmarking. I can compare lines, compare plants, compare even models of equipment very easily. But often this energy footprint data is not well understood across the broader organization. Just simply knowing how much energy does it take to make a case of this product or a pound of that product on this line, and how does it compare to one plant or another? And having that information available within the finance team and with the R&D teams, as well as the operations teams that we've been talking about up to this point, is very, very valuable. And so we make it easy to promote that data, to share that data with those teams in common business intelligence tools like Power BI and Tableau and so forth. But this is something we found that's been very, very valuable. So last slide here, and we'll open it up for questions, is some of the things that we've observed are the keys to having success, not just in a singular project of generating energy savings, but rather a sustainable program that is finding and generating new savings every month, every year, that is going to basically pay for your time and pay for the software that's in place to manage this on a year-by-year basis. The first is obvious, is an executive commitment to sustainability. And as I mentioned earlier, whenever you rack and stack business cases, if there's a quality problem, or if there's a production or a throughput or a downtime problem, chances are, on a dollar basis, on an economic basis, those projects and those problems are going to outweigh, on a pure economic basis, those of an energy savings project. So it has to be, even though the dollars and the payback are good, as we talked about earlier, the 30 to 90-day payback period is really excellent. The payback period on some of those other problems can be, in fact, even shorter with a greater ROI. So it's important that there is a commitment at the executive level that it is more than just the dollars and cents of energy savings. It really is about sustainability and about being able to go, if you're a consumer products manufacturer, to go to your customers and say, we're reducing our energy footprint on a global basis by 5% or more, and it's worth a lot more than the direct dollars for saving electricity, for example. And where there is that commitment, these projects can obviously go a lot faster, a lot smoother. The second key from our perspective is to choose a software platform that is built for engineers. Not that it's not built for data scientists or for software developers, because it can be built for those groups of individuals. But the important group in our mind are the subject matter experts, the engineers, the folks that really understand the equipment and the processes, that can take a platform and innovate with it to find energy savings and to not be encumbered by having to build software, to do research and development, or to become data scientists. It's a tough putt. Many, I guess, have tried, and some have accomplished that. But we think it's just better to focus on the engineers and empower the engineers that really understand the equipment, and that's where the best return on investment comes from. The third point is embracing digital twins, and really you should think that the primary benefit of building digital twins and having a digital twin strategy around the equipment, and this could apply to a commercial building as well as it would apply to a complex manufacturing facility. It's about being able to scale, and what the digital twin enables is to innovate by equipment type innovate by problem, and then use the digital twins to scale that across, potentially thousands of assets. It's really, really key to achieving the return on investment, and to do that in a sustainable way is the speed with which you can maintain and build and scale the solution is really centered around those digital twins. The next is thinking about establishing the business cases, because remember, this is just about taking data and applying analytics, and not necessarily, in many cases, doing a capital investment project. It's really about continuously identifying the savings, not as a singular event, but rather a periodic and continuous process that's happening every quarter, every year, to identify new business cases. Where's the next couple percent of savings coming from? And just doing that again and again and again and again. And in all likelihood, you will never run out of opportunities for improvement. And so working that process as a continuous process rather than a singular project is key to sustainability from our perspective. And the last point is committing to doing production pilots, as opposed to research and development pilots. Commit to doing things in production with real data, solving real problems, and then commit to operationalizing those results. Maybe it's only done in one facility before you do it in 100. Maybe you do it on one line and before you do it on 1,000 lines. But whatever the scope of that pilot is, that you're committing to doing it for real in production and actually operationalizing the results. We've seen this as really what separates those that are moving fast with this technology and those that are moving slow with this technology, is those that are kind of treating this like a science experiment are moving slow, and those that are making the commitment, success or failure, making the commitment to operationalize the results in a pilot are the ones that are moving fast and getting past pilots and scaling this concept into production. Okay, with that, I've concluded the presentation and like to open it up now for questions. We've got a few minutes to the top of the hour. But
Hi, this is Shannon. Can you hear me?
Yes.
Okay. The first question comes in, and it's: in manufacturing plant, API prefer to maintain a centrifuge 100 HP in operation, even without product, because of a possible reliability issue. Have you seen that issue?
I'm sorry, could you repeat? I missed a little bit of that.
A manufacturing plant, API,
Yep.
prefer to maintain a centrifuge 100 HP in operation, even without product, because possible reliability issues. Have you seen that issue?
Yeah, if I understand the question, I mean, it's similar to what I was describing around procedures for shutting down and starting up. It's, the part of the model has to take into account when we're going to shut something down, that it's going to be down long enough to justify shutting it down. Because some processes, if for example, if it takes 30 minutes to start up this vacuum pump, for example, it wouldn't make sense to shut it down when there was only a 2-minute downtime event. So in effect, the model has to build in those nuances. And if I understand the question, I think that's really what that's referring to.
It is great to see a short payback time. Considering the economic slowdown, quick payback projects are high on priority for organizations these days. For the facilities that do not digitally record energy consumption data and need to install logging infrastructure before incorporating the TwinThread solution, can you share the potential payback period?
So without metering, so it's going to extend the payback period because, you know, we have to infer much more from an energy perspective than would otherwise we would have the meters in place to learn from or to validate from. It would be highly unusual, highly unusual to find a facility that had no meters whatsoever. However, it would be very common to find a facility that had not enough meters, or you know, they only had one meter that spanned, you know, 30 pieces of equipment or whatnot. And that's why earlier I mentioned the concept of creating software-based meters, things that can take the process data, like, for example, this motor current or this flow or this machine speed, and infer the energy consumption from that. That's why that concept of having a software-based submeter is important and comes into play, because, again, very common that there are just not enough meters to provide the full payback. And then the last thing I would say is, so if the meters are in place and we are, as part of an analytics project, delivering a 11-day payback, there's enough room in there to go invest in some meters to install them. And maybe you dilute the payback to, maybe you dilute the payback to 6 months. Maybe you dilute the payback to 4 months or something like that. So there's room in there, given the potential to impact the process. There's room in there to make some of those metering investments. And we have customers that are doing that as well.
The data you considered for this case, is it line level data, equipment level data, and what was the data resolution?
Yes, that's a great question. So we often recommend, let's get all the data that's available. So that could be all of the data that's in a PLC, or all the data that's maybe even being historized into a historian. And that spans the meter data. It spans the equipment state data, the on-off data, if you will, as well as all of the process data, the flows, temperatures, pressures, currents, speeds. All of that can add value to the energy model potentially. And matter of fact, in the modeling step, one of the steps in modeling is to really examine all of the data and then narrow it down to only the parameters that have some bearing on energy. So our recommendation is to start with everything, and then the model will sort out what is actually important. But we want to get our hands on everything that's available.
Can you please suggest a short-term course where we can get trained on software which links energy efficiency and predictive data analytics?
I may have misunderstood. Could you repeat that?
Can you please suggest a short-term course where we can get trained on software which links energy efficiency and predictive data analytics?
So I think there are lots of courses available from a number of platforms that, if you're interested in data science, for example, you can get just virtually any of the popular online course programs can give you some level of education on that. To get the level of application level knowledge, around, for example, what TwinThread is doing, we offer education and materials as well as training to learn about the platform. This is not something that you're likely to get that level of training from a from a course. But if you have that interest in learning data science and sort of analytics in general, there are many online programs available for that.
Okay, our last question. How do you maintain connectivity across the planet with so many outside influences, i.e. weather or other disruptions?
Yeah, I mean, it's a great question. You know, one of the data sources for a lot of applications is actually the weather data. Whether that be a mobile asset or a fixed asset is pulling in the weather data, and that's coming from an external source and combining it with data coming from the actual process. If it's important, and there's a lot of processes where it is important, we make it pretty easy to pull in that data and marry it with the internal data, let's say.
Okay, so we're going to wrap up. I'm going to share my screen to close the meeting. And let me know if you can see this. We want to thank everyone. We have a few more announcements from AEE before we wrap up. As a reminder, you will receive an email with your attendance and certificate and a recording of this webinar. If you're interested in obtaining a copy, please send me your email or request it via email directly to me at shannon@aeecenter.org. AEE World originally was being held in Denver, Colorado, but it's going to be transitioned to the virtual event the week of November 30th. Please continue to check our website for event details. I'm also excited to announce that 2021 AEE East Call for Papers is open and was open last week. This event will be held in Boston, Massachusetts on March 24th and 25th. Please make sure to submit your papers at aeecenter.org before the deadline of October 23rd. Our next webinar will be Tuesday, September 15th, Sustainably Lowering Your Costs While Improving Reliability Should You Benefit from a Microgrid. Please look out for the registration invites that will be sent to everyone. Thank you again to our presenters. We appreciate your time and dedication. Please stay safe, and we hope each of you have a wonderful day. Thank you.